That was my attempt at music. It was terrible. Hello and welcome from my math science lab, which I'm recording from exactly like 2 minutes after the previous recording. Yeah. Um, we are going to try to take all the lessons we've learned about all the different types of equilibria and try to condense it down into a single tool which will help us tell the stability of the origin for linear differential equations, specifically in 2D, a lot more rapidly, and kind of help us sort of get our heads around, like, why were we doing all of this crazy stuff? Okay? In the backs of our minds, I always want to be holding on to the forms of the solutions to the differential equations. Those combinations, the linear combinations of the eigenvectors, and then e to the lambda t's. All right, and we have all the different cases, if they're repeated, if they're not, if they're complex, if they're real, etc., etc. All those things are necessary information. What we're doing right now is we're sort of developing a tool that, like, well, if I don't necessarily want to know the exact solution, but just generalized behavior, what we're doing now, condensing all the other information, will suffice. Promise. Okay. So the eigenvalues of our system were really the things that determined what was going on, right? The first major big division we had in these eigenvalues was the difference between when the solutions were real or when they were complex. Basically, did they oscillate with sines and cosines, the complex part, or did they just either grow or shrink in various ways without spinning around? Real. Okay. In the real scenario, we have two major divisions here. We have two distinct real roots, or we have one repeated real root. Those were the big things. Now, while we didn't necessarily say it like this, we have three distinct cases for when we have two real roots. Well, think about them, okay? We had where both of the roots were negative. Sorry. We had where both of the roots were positive, and we had where one of the roots was negative and the other root was positive. Right? Those are all of our cases. And what I'm ignoring for now are the additional cases for when one of them was zero, or if they're both zero, etc., etc. We'll get to that. Okay. Now we had a repeated real root. Okay, cool. And in this case, either it is negative or it was positive. That's supposed to be a lambda. The ugliest lambda I've ever drawn. Okay. Now in complex, we really only have three different cases. Okay. Alpha plus or minus I beta, where alpha is positive. Alpha plus or minus I beta, where alpha is negative. And the one that's kind of stuck in the middle, even though I didn't draw it in the middle, alpha plus or minus I beta, where alpha is 0. Now remember, alpha is the real part of the complex. It is the part that goes into the exponential term in our solution. So alpha positive means that I'm exponentially growing while beta is telling me I'm oscillating. So my oscillation is getting bigger, bigger, bigger. Spiral source. Alpha plus or minus I beta, where alpha is negative, means the exponential part is e to the negative number, which means while I'm oscillating, I'm getting smaller and smaller and smaller. And then alpha plus or minus I beta, where alpha equals 0, means that e to the alpha t term is just the number 1. And so I just have sines and cosines, so I have some sort of like oscillatory periodic solution. Our centers, right? Let's go ahead and write all these down. So here we had a spiral source. Here we had a spiral sink. Here we had a center. Okay, cool. This guy right here, where both of my real eigenvalues, the one all the way on top, where both of my eigenvalues were negative, okay, we call this a nodal sink. It didn't spin around, it just sort of went there. And we either had the u like this or the u like that, depending on their relative magnitudes. Lambda 1 and lambda 2 are both positive. We call this a nodal source. and then one of them negative and one of them positive. We called this a saddle. Remember where it drew in from one direction and then out to another. So we had these kind of whoop, whoop, and I'll do some more drawings. I promise, I love drawings. And then this right here was a degenerate sink and a degenerate source. We couldn't have some sort of degenerate saddle. Doesn't really work that way. I guess we do have a degenerate saddle. It's when one of the eigenvalues equals 0. Get there. Okay. This is what I want us thinking about right here. All of this stuff. So I want to tackle this first division first. Okay. Now, we all know that if A is A, B, C, D, we've done enough of these so far that we know that lambda solves this polynomial. Lambda squared minus A plus D lambda plus AD minus BC. Now we also know, because I've written it down a bunch of times, if we define the trace of A to be tau, that is equivalent to A plus D. And the determinant of A, if we call that capital delta, why, that's AD minus BC. And so if I went about solving this, lambda equals the trace plus or minus the square root of the trace squared minus 4 times the delta, and everything, good Lord, everything over 2. All right. So now if we reference this red branching, this red fork right here, the difference between real and complex, where does that come from on this expression for lambda? It's all controlled by this bad boy right here. If it is positive or it is negative, that's how we get the real or the complex. Okay? Interesting. Let's come back up here. All right. Now, whether we're real or we're complex, we have sources or sinks, and they have to do with positivity or negativity. Okay? So let's look at sinks first. Okay. A nodal sink occurs when lambda 1 and lambda 2 are both negative. Okay, cool. How does a spiral sink occur? Oh, it's when the real part of this guy right here, when it's negative. That's sharing something in common. Okay? In a different green, but still a green. Okay, let's look at nodal sources. Nodal sources occur when both of my lambdas are positive valued. Cool. What about a spiral source? A spiral source happens when the real part of that complex eigenvalue is positive. Aha! There's something in common there. That's really cool. Okay? If we, therefore, study this guy over here, where is that positivity, negativity coming from? Well, first off, if this were complex, just if it were complex, actually, even if it's not complex, I can always write it like this. Right like that. Okay? Now, if it's complex, the real part comes from this right here, tau over 2. And so its positivity and negativity depend on the positivity or negativity of tau. But now if tau's negative, then alpha is negative. But what can we say about lambda 1 and lambda 2? Well, it depends on delta in ways that I will describe a little bit more in a minute, okay? But we can clearly see that for both of my eigenvalues to be positive or negative, this bit, tau over 2, needs to be related to this bit in very particular ways. Okay? So this is interesting to me. The final bit we've got right here, and I do mean final, okay, is this guy right here, saddles, where they are of opposite sides. And so again, that's going to depend on this delta and what is the relationship here with this number. Okay, I want to investigate all three of these sort of bits and pieces in ways that might be beneficial to us, so we can see that everything depends on the relationship of the determinant of our matrix with the trace of our matrix. Okay, and by standard convention here, I'm going to make this horizontal axis my trace and this vertical axis my determinant. Right? This is my trace determinant plane. Okay, great. Now, if we look right here, the first bit here, this tau squared minus 4 delta, this tells me if I'm real or complex, right? So let's work with that right down here. Tau squared minus 4 delta. Okay, great. If it's positive, we have real roots. And if it's negative, we have complex roots. What's in between of positive and negative? Well, when it equals 0. Now, if I look at how I've got this plot rearranged here, I'm treating tau as my independent variable. So I'm going to solve for delta, and it's going to equal tau squared over 4, which is a parabola. That is not a bad parabola. Okay, this is the parabola tau squared over 4. Okay. Now, tau squared minus 4 delta being positive, which would mean I'd have to have a real root, means that tau squared over 4 needs to be bigger than delta. So what that tells me is everything down here. Oops, let's not do it that way. Boop, boop, boop. Yeah, okay. We've got this here. I want it highlighted. There we go. Everything down here. This is the case where I have, come here, real roots. And then everything above the curve is where I have complex roots. So everybody underneath this red line means that my eigenvalues are real. And if I'm below the red line, my eigenvalues are real. If I'm above the red line, my eigenvalues are complex. Do we understand that? Do we kind of get that? So what I'm going to do here, actually, let's get rid of that. That was a piss poor idea, but we will keep that. Okay. So that's our first major dividing line. Now we look back up here. This tau over 2 determined whether or not the real part of my complex eigenvalue was positive or negative. If tau is positive, then we had spiral sources. And if tau was negative, we had spiral sinks. Spiral sources. Spiral sinks. And then if tau is 0, then my eigenvalue could be written as plus or minus, what would it be? I want to write it like that. Yeah, we'll just write it like this. Square root of 4 delta I over 2. Square root of delta I. But anyway, it would be purely complex. And so along this axis right here, I'm tilting it for myself, but you guys, it's not tilted for you. This is where the centers are. Those nice circle periodic solutions. They live right there on the dividing line. I hope that we can all see that. Okay. The next bit is a little bit more tricky. Okay. Because I want to handle the case of all these real regions underneath the red line there. All right. So if, let's go here. If lambda equals negative, or not negative tau, what the heck? Tau plus or minus the square root of tau squared minus 4 delta all over 2. All right. Let's make two decisions here. Let's say there's a case when my determinant is positive, a case when my determinant is equal to 0, and a case where my determinant is negative. Right? Those are all my possible choices here. All right. If the determinant is positive, then think about this quantity right here. It is smaller than tau squared, correct? It's just not anything fancy. Cool. Which means the square root of this is smaller than the square root of that. Sure. Which means that square root bit is smaller than tau. Okay? So now if tau were a negative number, then I'd have a negative number plus or minus another number which is smaller than it. And I do mean not less than, I kind of mean smaller than. This less than sign's a little bit abusive with notation. I mean smaller than, okay? So something like -3 plus or minus 2. They're both negative, and that will always be the case. So if my determinant is positive and my trace is negative, both of my eigenvalues are negative. But what about when my trace would be positive? Well, I'd still have a positive value plus or minus a number smaller than it. Which would mean that, well, I'd have a positive number plus a positive number, that's positive. Or positive number minus a number smaller than it, that's also positive. Okay, so if the determinant is positive, and we're in a real root situation, tau being on the right or the left tells me if they are both positive or both negative. So that allows me to denote this region right here as nodal sources, and this region right here as nodal sinks. Cool. Good Lord, next page. Okay. What if delta equals 0? Well, then I'd have trace plus or minus trace divided by 2. And so I'd get trace and 0. One of my eigenvalues would be 0. What did we get there? A line of non-isolated equilibrium. Okay. Reference the previous video if you don't remember. Okay. Non-isolated equilibrium. That's that whole axis right there, because that's where my determinant equals 0. Groovy. What if my determinant is negative? Okay. If the determinant is negative, then tau squared minus 4 delta is actually bigger than tau squared. Which means the square root is bigger than tau. That last bit should be an equal sign. Okay. So if tau were a negative number, plus or minus a number which is bigger than it, well, one of them would be positive and one of them would be negative. If tau were positive, plus or minus a number bigger than it, one of them would be positive and one of them would be negative. So, whoops, regardless of which side it's on, everything underneath here is a saddle. Okay, and I promise you I'm going to make a version of this picture which is a little bit prettier in just a second. Okay, so we've covered basically every major region and all the dividing lines except for the red parabola there. What happens at the red parabola? We are transitioning from real to complex, which means I'm going from 2 distinct real roots, the discriminant being positive, to 2 complex, the discriminant is negative. So my other case is that the square root bit is 0, which means I have repeated roots. So all along the curve here is where we get degenerate nodes and stars. Because remember, stars was one of the special cases that we could get there. And so this kind of puts everything together. I want to draw it in a little way that makes it just a little bit clearer. So I hope, first off, that breakdown of all those cases makes sense to us on where they fall as far as the relationship between my trace and determinant are concerned. Okay, first bits first. We're going to draw this, which is tau squared over 4. Okay, so don't think of this as x and y. This is the trace and the determinant, okay? And what I'm going to be drawing are little vignettes, okay? So let's handle the case where my trace is negative and the determinant is greater than tau squared over 4. So I'm above the red curve, trace negative. This means I should have spiral sinks. This means that in a characteristic way, my equilibrium point is stable and I spiral in towards it. So I'm going to just draw a little vignette to remind me. Now, what if the trace is positive? Well, that means my equilibrium point is an unstable spiral. Cool. What about if my trace is 0? Well, those are centers. So we just orbit periodically around my equilibrium point. Ta-da, ta-da, ta-da. Now, what if I'm below the red curve, but above the tau axis, and my trace is negative? Well, that means in my little vignette, both of my eigenvalues are real and negative. So I've got a stable node at the origin. Remember, these are all little vignettes. I don't have equilibrium just scattered around whatever this plane is. Okay. What if my trace is positive? That means I had 2 real roots, and they were both positive, which means in my little vignette here, on my equilibrium, all trajectories flow away in a nodal fashion, and I have an unstable node. Cool. What about on this axis here? It means I only had one characteristic direction, and everyone else kind of pinwheels around it. This is my degenerate node, and it's stable. Over here, my degenerate node would be unstable. And again, I get this sort of pinwheel action going on. So far, so good? Now, everything below the horizontal axis is the same. When my determinant is negative, then both of my eigenvalues are of different sign, which means I get saddle nodes, which should look something like that, whatever their characteristic directions are, their eigenvectors. So far, so good? Finally, along this horizontal axis is where I have a line of non-isolated equilibria. So over here, I would have a line that attracts flow to it. In itself, straight lines. Or over here, I would have a line that repels trajectories from it in straight lines. And this is basically everything. Right here is where madness lies. It's really hard to tell what the heck is going on there. But this is our trace determinant plane. This lets us do all sorts of things, all right? So let's just pick any matrix. Pick any matrix. Pick numbers that you want. I'm going to go 3, -2, sure, whatever, 1, and 7. I don't have notes on this, okay? And I'm going to say that this belongs to a system of first-order differential equations where this is my coefficient matrix. Now, I want to know what is the stability of equilibria, a basic, vague idea of what's going on, okay? Well, what I can do is the following. My trace is a 10. And my determinant is, what is that? 21 minus negative 2 is 23. Okay, cool. Now, what is my trace squared over 4? Well, that's going to equal 100 divided by 4, which is 25, which is bigger than my delta. So what does that mean? Whoops, there's the picture. Okay, trace squared over 4 is bigger than delta, which means I'm below my red line. Okay, my determinant is positive, which means I'm above the horizontal axis. My trace is positive, which means I'm to the right, which means I'm at an unstable node. So I can write, without knowing anything else, that 0, 0 is an unstable node. Okay, to cover that again, my trace squared over 4 being greater than delta means I'm below the parabola. Delta being positive means I'm above the horizontal axis. And trace being positive means I'm on the right-hand side. And that's how I can conclude unstable node. Pretty cool, huh? I didn't even have to give you the eigenvalues. If I want to be able to draw this, I need eigenvalues, I need eigenvectors, I need to be able to do that, right? Because at this point right now, I might be tempted to draw this, okay? I might be tempted to slap down an axis. As soon as I do, the only thing I know is that my equilibrium point's at the origin. Do I know where my characteristic directions are? No. Do I know if I'm coming upward or kind of downward? No, I don't know any of that, but I know it's an unstable node. Now, when would that possibly be enough information? Well, if X and Y are describing, let's say, species in an area. Oh, 0, 0 is unstable. The system won't go extinct, according to this model. That's pretty useful, right? Let's jot down another set of numbers. Again, I don't know what's on this. Let's go. I like negative 4. I like 8. Let's pick an ugly number. 3/7. Oh God, why did I do that? And 14. I don't want 14 there. Let's go with 1/4. Cool. That's stupid. So what is my trace? My trace is negative 3.75. What is my delta? What is that? Negative 1 minus 24/7. Yeah, that's right. Okay. Okay. My trace is negative. Do I expect stability or instability? I should probably expect stability above other things. But my determinant is negative. I'm going to write stability. And by that I mean sink. My determinant being negative immediately means I'm a saddle. And so what this is telling me is one of them is growing and one of them is crashing. Which ones? I don't know, right? Do I know that it looks like this? Or this? Or some wonky one like this? Whoops, I just drew a nonlinear system. We're not there yet for crazy wonky ones like that. Here we go. I just needed an eigenvector to guide my pen so I didn't go too crazy. I'm trying to draw a trajectory here. Why aren't you letting me draw a trajectory? There we go. Arrowhead. Okay, cool. Draw another trajectory. Okay. Again, in the case where these were species, This is important because in this case, species X can persist forever. In this case, species Y persists forever. In this case, they both persist forever. It's important to know because the difference can mean everything. Okay, but what we do know is that we don't have complete system extinction because it's a saddle, which means the origin is unstable. Okay, I hope this helps. That's the trace determinant plane. That's what's going on. We're going to be starting with some nonlinear stuff in like a day or two. It's going to be cool. Okay, bye-bye. Where's the